I think the most beautiful thing that photography offers us is the possibility of seeing, always on the same sheet of paper, and always with the same size, and let's say up close, both the general and the detail of a monument or object any, with consequent enlargements, which is very different from observing. Take the case of the church itself, from the street, both because it is sunny, which usually dazzles us and does not give us the ideal light, either because there is traffic, either because we get tired of standing and looking at the monument, or we can't get to see the details. The ideal is to import the three-dimensional model into a space. We say within reach, also because, set between us, the stereo vision works very well only at a short distance, and because the variation of the angle formed by the visual axis is very large, and because when we move in this space, the brain better appreciates the changes in the angle. In fact, when there is an object very far away, think of a car overtaking, as long as the other car is very far away, you cannot evaluate its speed. Happen to start overtaking and notice that the other car is very fast. Or don't overtake and the car approaches very, very slowly. Precisely because the variation of the angle of the visual axis is very small. That's why, this also caused the machines to fail. Stereo cameras, because the reduced base made the stereo effect vanish. And it did not differ much from monocular photographs beyond a certain distance. It was worth using simple photography. Therefore, returning to our discussion, the ideal is to bring the three-dimensional optical model of the photographed object to our table and, to do this, artificial stereoscopy comes to us. What does it consist of? Following the scheme of a photographic shot, it was clearly schematized, because the camera projects, with the lens, the image upside down on the film. In this case the image is positive, therefore it is imagined that the lens projects, as in the case of the model on the screen, a certain point P, which is recorded on a pair of frames. When we reproject the 2 points P1 and P2 recorded on the frames from 2.01 and 02, the rays will meet at the real point P. So we could rebuild this way, projecting all the points on the slabs and reprojecting them, the detected monument. If we now try, after having taken the shot, in this case of only 1 point P, we try to bring the two plates closer together, and reduce, in essence, the distance between the projection points, which we will call the base, and we reproject the point P, we easily realize that the reconstructed point P is much closer. With a trivial geometric demonstration, we will find that the reconstructed model is reproduced on a scale corresponding to the scale of the base. Practically, if I take a shot with a base of 60 meters, and project with a base of 30 meters, I will have a scale model 1 to 2. If I project with a 6 centimeter base, I will have a 1 to 10 scale model. If the base is 100 times smaller, I will have a scale of 1 to 100. Another premise, which we must immediately make, is that the beams of rays, which project the points, must remain unchanged during the restitution phase, that is, when they are projected in the opposite direction. To this proposal we make a very simple decision. We fix a rule. I have the interpupillary base of 6 centimeters. The visual axes that intersect in this way. So if I hold the camera, in order to take 2 photographs, with coplanar frames, I can simulate the case examined quite well. This case is called normal case. So we start with 2 cameras with parallel optical axes. We photograph and return the model in this way, and we will certainly have the model reproduced in the scale in which the base is reproduced. Of course, if I now do a 20-minute base shot, and I observe with the base of 6 centimeters, I will see a model as it would see who has an interpupillary distance corresponding to 20 meters. At this point the speech is very simple. I observe I am very good at taking measurements in this space, let's say within reach, for the simple fact that since baby, every day I'm forced to take items. And every time I take an object, I have to detect the position. So the brain controls the hand to take it, and I realize that, apart from the first months of life, then it became very good. I've never been wrong. Even if I have to take a needle, I do it quite well. So I try to always bring the model back to this space, where I am very good at detecting, appreciating measurements. To do this there is a very simple speech. The minimum viewing distance of an object is on average 25 centimeters, so I make a ratio between 6 centimeters and 25 and roughly 1 to 5, on average. Then I always consider the interpupillary distance of 6 centimeters and the maximum distance of an object that I can touch, let's consider 1 meter. And I will roughly have the ratio of 1 to 20. So I establish a very simple rule, the base must be between 1.5 and 1.20. The distance at which the object to be detected is located. If the object is 300 meters away, I average and consider 110, then I take a photograph, take a nice 30-meter walk and take the second photograph. I will have the model photographed, which is 300 meters away, like a plastic on hand. And in fact anyone, looking at aerial photographs under the stereoscope, says the first thing, it looks like a plastic, because it's a plastic. But a city, seen from above and photographed in this way, would risk showing very small houses, and would not allow me to appreciate its height. To do this, I call the second scheme. I vary the focal length, that is, I take the photograph with a certain focal length and observe it with a much larger focal length, so I have a very elongated model. At this point, the use of the stereoscope is only important because the viewing distance set by the stereoscope is well determined. If you were to use glasses, or with red and green filters, or with polarized lenses, with polarized light or those with alternating images, while I watch them, I probably approach or move away from the screen, in this case not stopped by the stereoscope. By varying the viewing distance, I will see the model that can be lengthened or shortened. It is true that this makes me very comfortable, because if I have to appreciate a height more, I move away and, if I don't care, I can get closer, but, of course, I will not have a constant three-dimensional image. Then there is one last chance. If I make a red sign, so to speak, on the tip of the bell tower of the photo on the right and I make a sign, equally red, on the corresponding point of the photo on the left, I will see, in the stereo model, a red dot on the tip of the bell tower. On this principle is based what is called in mobile brand photogrammetry. In the other scheme, but we will talk calmly later, we immediately see that I can make a dot move on this three-dimensional optical model, this reference brand, the mobile brand is called. In what way? If the brand moves horizontally on both photos, I get a horizontal shift of the mobile brand. If the two brands, on the two photographs, move vertically, I get a vertical movement of the mobile brand. If the two brands move closer or farther away, I will have a shift in the third direction. If I can know the coordinates of this point, you understand very well that it will be very easy to trace the coordinates of the points identified, and therefore also to measure the distances. applying the formula of the distance between 2 points in space.